All right. So I found this time machine. I'm just going to go through these really quick because we only got 20 minutes. And not some hippie good doer time machine, but I want to get one where I go back in time and bring some good weapons with me. So no, seriously, Wi-Fi to shared media. Remember that? You know, 1980s, 1990s, good times, session hijacking, DNS hijacking, all the good times with the local LAN. But I mean, it would never be that easy still now, would it? I mean, everyone encrypts their Wi-Fi networks, right? Really? Right? I mean, companies have to be smart enough by now to do that. You'd never take your company machine from a secured network to an insecure network. Starbucks, airports, the gym, the hotel, here. So let's bring in the troops. Lorcon, injection library, now with a new improved API that actually, you know, is interesting enough to use. Metasploit, Racket, and additional Ruby libraries. So why Lorcon? Writing the same injection code over and over again really sucks. Writing custom apps for every driver's quirks really sucks. Writing apps for every operating system really kind of sucks. Hopefully, Lorcon, it doesn't suck. Why rewrite it all? Because the first one kind of sucked. The new API is modeled off of PCAP, so it's much simpler to use. And translating apps that do standard layer 2 PCAP stuff with Ethernet should now be really easy to do with Wi-Fi instead. So right now, you need Linux, and you need Mac 802.11. Eventually, Lorcon 2 will expand back up to all the drivers supported by the old Lorcon, but I wrote it for the con, so it's not done. And there's unfortunately no good way to do injection on Mac under any drivers, unless you write a complete user space driver stack. So using Lorcon 2 in Ruby, really simple interface. Require Lorcon 2, create a new interface. It'll automatically figure out what driver you're using. It'll figure out what modes it needs to set. It'll figure out if it needs to create injection VAPs. You open it in injection mode, and then for each packet, do some fun stuff. You can pull a .3 equivalent packet out, so you can feed it to all the existing libraries that expect 802.3 Ethernet frames. And you can dump it directly into Racket to decode with a nice Ruby-based decoding. So we can make a packet the same way, and we can make a Ethernet frame and then translate it to 802.11. So making a packet, just make a new Racket, set your Ethernet addresses, set your IP addresses, set it up like you normally would, generate whatever you want, and turn it into a .11, and it'll go right out, and you get to have some fun. So it's really easy to decode .11 and manipulate it now. Why aren't people doing this more often? It's really only marginally more difficult to make all the awesome old attacks from the 80s and 90s still work. We probably just forgot how awesome most of them were. Now that we're in switched Ethernet, we don't get to play around with that anymore. So now we control layer 2. I don't have to own the internet, I own your internet. Spoofing your DNS, really easy. Spoofing ARP without the network seeing it, really easy. TCP spoofing, haven't we been here before? Yeah, about 5 years ago, Airpone came out. Thanks to Toast at DEF CON. TCP replacement, targeting HTTP over Wi-Fi. Why isn't everybody using this? This is really, really awesome. And it's not just for shock porn anymore. If you don't get it, ask the person next to you. They'll be happy to explain to you, I assure you. So, of course, users will make bad security decisions. They're not security people. The OS really doesn't help them. And we're using layer 2 to expose the layer 8 problem of users can't make decisions. So, right before this talk, OpenOffice decided to eat half my slides, so it's a little adventure. So users really don't stand a chance. Even smart users, people here, aren't going to be able to beat an ODay if you go to load a web page and you get, I don't know, latest Flash exploit or something. This breaks any sort of user trust model. Any site you go to can have replaced content. You don't know if you're not on an encrypted link. Any other browser exploits, you don't know. Any other TCP service exploit, why don't I just spoof IMAP, hijack your TCP session, and feed you a email message that exploits your reader? So this is like car Metasploit, where you can hijack every AP, but it's even sneakier because you're not actually hijacking any APs. So nearly all major sites include a whole pile of little JavaScript helper files, or Google Urchin, or jQuery. So what do we get if we replace them? Anything we want to do inside your browser in the security context of the page you're looking at. So remember our Snakes VPN paper about a month ago. He figured out that you can control the caching headers on files and make them stick. So yeah, here's the Urchin.js for Twitter. go ahead, request it, it's good. You know, nothing will happen to you, won't load an iframe or anything. So you set a cache header on that. Say you set it for 10 years. User would never go back to corporate and go on a social networking site, would they? Yep, so now we get an iframe execution inside the corporate network with the stuff we fed them over Starbucks network or whatever. Downside, I can't spell downside is the first downside. The second downside is that you have to know the file you want to replace ahead of time, but that's not so hard with common sites like Twitter, Facebook, Google Urchin, et cetera, et cetera. You already know all those files, you copy them, you drop a little iframe at the top, and there you go. So the Metasploit module, it's actually not vaporware. So how do we implement this inside Metasploit? So we get the Lorcon 2 module, set it up as a threaded auxiliary server like the HTTP spoofer and whatnot. Add in some regex matching, use YAML so we can replace however many files we want with one config. And I'm not even going to pretend that the demo gods are going to smile on me today, since OpenOffice wouldn't even. So here you go, you get Courier font screenshots pasted into OpenOffice. But so there you go, you can set the interface per normal, load it up, set the response. You can do quick responses based on the CLI in Metasploit, or you can do complex responses pointed towards files on your file system and whatnot, and set it to run. And OpenOffice ate my screenshot page showing that actually worked. So DNS stuff. DNS is obviously, it's just UDP. It's really easy to target specific users on a Wi-Fi network and hijack just their DNS requests. You don't have to ARP spoof the DNS server. You don't have to DHCP spoof to give them a different page. You don't have to worry about any of that. This also works great as a Metasploit module with YAML configs. So, overwriting DNS. Yeah, it's pretty much that's the entire code with a little bit around it. It's really that easy. The RubyNet DNS module does it for us. Grab the payload, grab the UDP out of it with Racket, look at the DNS, set the DNS header as a response, give them back their question as a INA with any IP you want, and there you go. So how does this interact with IDS systems? Lots of wireless networks try to prevent users from talking to each other so that one user can't directly ARP spoof another user on the network, etc. Nothing can stop anyone from spoofing the AP and talking directly to the user, though. If they think they're associated and they think the packet's coming from the AP, we win. Open and WEP networks are essentially impossible to deal with securely because you can't do per user crypto and you can't prevent an attack from spoofing the access point. Wired side IDS systems will never see these attacks because they're not bridged to the wired network. We're going directly spoofing the AP to the user. The traffic will never hit the access point, it'll never hit the wired network. Some wireless IDS systems may also ignore them. It thinks it's coming from itself. They have to be pretty well aware of what's going on the network to determine that the packet isn't coming from a legitimate AP. So where are we going to go from here? Finish cleaning up the Metasploit modules, get them committed into Metasploit, hopefully sometime very soon for that. Add WEP and WPA injection to Lorcon, and expand the Metasploit layer 2 stuff so that all the existing attacks will now work with wireless. And expand AirPwn to work with large files, which it doesn't currently. And then also link to automatically generate Metasploit payloads for the responses. So injecting on WEP will be as easy as injecting on Open if you know the key, because all users have the same key. So you just generate the key stream, write the packet, it goes out to the user, you're done. Plenty of ways to get the key. Aircrack will get it to you in about 3 minutes. Injecting on WPA PSK. PSK is slightly better defined. There's per user keying. However, if you watch the user associate and you know the keying setup of the PSK and the network SSID, then you can just spoof traffic to them directly anyway. I mean, it's a good thing we can't just kick users off the network and watch them reassociate and get that info, right? Oh, too bad. Broadcast uses common keys between users, so once we get the broadcast key once, we can use it repeatedly. And the module will need to support both TKIP and AES. How am I doing on time? I got 5 minutes. All right, I'll go real quick through some other stuff since my other slides got eaten. So let's mix this up a little more. I'm just going to go really quick so we can fit in a few questions. What happens when two packets in the same TCP window with the same sequence number with overlapping ranges of different sizes hit the stack at the same time? In Linux, it means the stream comes out with the overlapping versions of the two packets, or I'm sorry, the non-overlapping versions of the two packets. So what happens when you request a web page? HTTP comes back with a lot of headers. That looks like about 200, 300 bytes. What happens if we send an overlapping packet that races the official response and use short headers? Yeah, we get to spoof before the page. So the response coming in is my short headers, double new line, HTTP data, which will then include, say, a JavaScript include, and then whatever official headers came back from the remote. So you end up with something messy where you get sort of you get the script source and then you get to the other headers kicking around. So there's a few limitations there, but if you get that executing, if you get the JavaScript executing, you can then just clean up the inner HTML of the document reference, and by the time it presents to the user, it looks perfectly legit. Only now there's blind spoofed JavaScript include on the top of every web page. So there's some problems. We don't know the content length. This actually turned out to be the biggest problem with all of this. Chunked encoding, you still have to terminate the last packet, so we can't use that. And there's no way to know the length of the original headers since we overwrote them, and we have to beat them so the time we're generating the packet is prior to the time that we could ever conceivably know the length. So there's a few ways around it. I think I've seen this file before. Say Urchin or jQuery or anything like that. We just remember how long the headers are for that server, so the second time the user reloads, whatever page they're reloading, we know where the data begins, and we can generate a custom overlay header that fits nicely on the top of it. Now we don't need to know the original, we still don't need to save the original content to contaminate it with the JavaScript include, but we do need to see it once. We could also try to guess at the offsets. Inject an overlay immediately, don't append a content length, which means the browser's going to keep the connection open trying to read more. Remember the pairs, and then when we see the real response come in a couple fractions of a second later, we just send a fin and close down the connection and spoof it. It works sometimes. Fortunately, offsets are easy for us to guess sometimes. So if we've remembered what those files were, we can just keep jumping along them. So we can also use the same trick to append TCP streams. What does an HTTP 1.0 stream look like? Give me GET request, response comes back, HTTP, oh, that was good to me. I put a 1.1 header on a 1.0 example. So it comes back with a bunch of headers, a bunch of data, and a fin packet. So what happens if we beat that fin packet to the client? Just what you'd hope, we now control that stream. The remote server isn't going to send any more fin packets. The fin packet that got there is going to get discarded since it's out of sequence. And browsers don't seem to care that much about content length on HTTP 1.0. So you can just keep appending to the end of every web page that gets requested if you beat the fin. So you can just append a JavaScript after the HTML, and most browsers will just happily include that too. So winning a fin race, unfortunately, is really hard, especially on small single packet responses. I've only seen it work about 10% of the time, but still that's 10% of blind owning of web pages. It gets really mad with HTTP 1.1 if you don't detect that the connection is actually a multi-request. And you can't control the caching attributes there, so you don't get to play around with controlling the cached data coming from there. So it's one time only. You can affect it while they're nearby. And that's about it, and should leave me about 2 minutes for questions. Anyone? No? A pity question, hooray.
No, actually, so like your Magnet does a pretty good job of picking up weird stuff like this. And I know Cisco WCS 1.5 is actually doing a really good job of picking stuff as well. Do you have any mitigating strategies against subverting that yet?
I haven't looked at that yet. Yeah, all right.
The big question was y'all.
I may work for a company that may make wireless IDS systems, so answering that question isn't one I'm particularly happy to do. It depends how the detection works. I'll repeat it for people who couldn't hear. The question was, what about Cisco IDS and Air Magnet detecting it? What they...
Cisco IDS, Cisco Wireless.
Cisco Wireless.
They have a WCS server.
Right, WCS. So basically, most of the IDS systems detect spoofed APs by beacons. So that's out because we're not sending any beacons. There may be, you can also detect by sequence number on the 802.11 packet. It depends whether or not they're able to track them quickly enough and whether or not we're able to spoof them quickly enough, if they even detect by that. I mean, most of these things are a single data packet sent to the client. The other trick for possibly mitigating that is using a very low power radio with a very directional antenna. If you bounce that data packet directly at your target client and the AP just doesn't see it because you're really quiet, then they're never going to be able to do an IDS against it. At that point, it's totally on the client side to correctly handle whatever funny packets are coming at it.
Unless you have one more.
Any other questions? Got one more. You're just in time.
Why is the IEEE ignoring the attacks against WPAPS, which is the regular
The question was, why is the IEEE ignoring the attacks against WPAPSK? So I assume you're talking about like the cow patty attack, where the attacks basically you take the SSIDs and you take a huge dictionary and you pre-compute every possible value. So then when you see the SSID once, you can just do a lookup instead of a brute force, because there's really no defense against a brute force attack. Oh, right, no, an IDS definitely wouldn't pick up an offline attack like that. But, I mean, it's really hard to defend against an offline brute force attack. If someone's willing to devote a terabyte of hard drive space and, 20 NVIDIA cards to it, I mean, the IEEE has effed up some things like WEP before, but there's not much you can do when someone's going to put that much power against it. There's no that flaw isn't a fundamental vulnerability in PSK. Or it isn't a crypto vulnerability in PSK. It's a fundamental problem in in just how the exchanges happen.
Okay.
Thank you.